Okay. But here we go. I have this system of equations. So W1 and W2 are just variables. Think of them as X and Y or whatever. So I could go ahead and solve this using methods from like chapter 5, right, where we solve systems of equations. And so generally, I would say use a matrix to solve most of the time for these sorts of situations. But in this situation, I think we actually get kind of lucky because, you know, if you're going to come and solve this, look really close at these two equations. We might notice something if we compare these two equations, is that they're just negatives of each other, right? This is negative a fourth W1 plus 1/3 W2. This is positive a fourth W1 minus 1/3 W2. So they just differ by a sign. And so like if I add them together, I'm going to get an equation that just says like 0 equals 0. And that's useless. I mean, I already know that, right? It's redundant. So really, I kind of don't need one of these equations. You know, I could kind of just like get rid of this one. You know, it's more than I need. So in this particular example, at least, I don't need this last equation. I just need these two. If you don't like that, I mean, go ahead and set up your matrix with 3 rows and whatnot, and row reduce. You'll find that you'll end up getting a row of all zeros, in which case you didn't really need the last row anyway. So I'm going to get rid of that equation, and we're really just going to look at these two equations in my system. So we're going to solve this system here. And since it's a system of 2 equations, I could do a matrix to row reduce to solve it, but I think what I'm just going to do is instead, let's do like substitution or something. Or maybe I will, or like the elimination method or something like that, just for fun. I'll do another example in a moment where we do a matrix. But for now, let's just look at a different method. So let's solve this system of equations. And then whatever we get will be our answer. That will tell us what W should be. So let's solve this system. So I don't know, if I was going to do the elimination method, I want to get like, maybe I'm going to cancel out W1. And so I want these coefficients to be opposites. So maybe I would multiply the second equation by 4 to get -1 in front of W1, so that these guys will cancel. So let's multiply the second equation by 4. And what will I get? I'll get negative W1 plus 4 over 3 W2 equals 0. I'll get this. And now I'm going to add these two together. And what do I get? Well, these guys cancel, and I'm going to get 1 plus 4/3. That sounds like 7/3. W2 equals 1. Hopefully I did my fractions right. 1 plus 4/3 is 7 over 3 times W2 equals 1. So if I solve this for W2, I'm going to find that W2 equals 3 over 7. So I'll divide both sides by 7 over 3. That's the same thing as saying that it's 3 over 7. So on the one hand, W2 is 3 over 7. So what's W1? Well, keep in mind, the two numbers have to add up to 1. So what's 1 minus 3/7? Well, that's 4/7. I highlighted them in different colors, but that's fine. So W1 is 4/7 and W2 is 3/7. So in conclusion, we have now found the stable vector. The stable vector is W equals 4 over 7 and 3 over 7. That's my probability vector, which is the stable vector. Okay, cool. So we found our first stable vector. And we did it with an example that I introduced like last week. So anyway, I'm going to pause here and ask, are there any questions about that process? Okay, so it doesn't sound like there's any questions. So I'll go ahead and summarize the process, and then I'm going to do another example that's a little more complicated to illustrate further how this works. So let me summarize what we did. Just so it's clear what steps were involved. So here is our strategy for finding a stable vector. Strategy for finding W. The very first thing we did is we wrote down a vector like this. we basically made a bunch of placeholder variables, W1 up through Wn. So the number of W's you have here depends on how many states there are in the Markov chain. You'll have one for each state. And we also know that when I add them all up, I get 1. So we write this down, write this vector full of variables down, and our goal is to find each one. Once we do that, we will basically write out W times P minus I equals 0. So we will just write this whole thing out. We'll do what we did before. We'll find what P minus I is, and then we'll multiply this with whatever we get for P minus I, and we'll set that equal to 0 and see what equations that gives us. So this gives a system of equations. Along with the additional equation, which tells us that the sum of the W's is 1. So the equations that I get from writing this part out, along with this equation, give me a system of equations. So then we just solve the system. Once I solve the system, that tells me what each variable W has to be, and therefore I then know what the stable vector has to be, because now I know all the entries. And so the only caution I might give you is just to pay attention to which W is which. These W's are numbered, so they come in a specific order in the vector. And so it's important that you get the order consistent. That last one I found W1 and W2, it was important that W1 came first and then W2 came after it. If you write them in a different order, you will be wrong. They represent specific probabilities for a specific outcome in the correct order. And so we want to make sure we keep the orders consistent. So that's like my only caution here is be sure you're paying attention to which WI is which and that you write them down in the correct order as you go. So again, you might get all the right numbers, but jumble up the order inside of the vector and then you'll be wrong. It won't be correct. So the order very much matters. That's just kind of how vectors work. Okay, so this is our process. Write down the W vector with placeholder variables that add up to 1. Write out this equation, W times P minus I, using this and whatever P minus I is. And then that'll give us a system of equations that I can then solve using methods from chapter 5. Okay, so I'd like to do another example just to hammer this in a little more. You can never do too many examples. I'll do one that's a little more complicated, or we'll be forced to do row reduction, which is good. So maybe it's been a while since we've row reduced anything. Let's see, here we go. I wrote this down here. So here's our next example. And so I'm just going to give us the transition matrix. So I'll just give us the transition matrix for this guy. It's the following. It'll be a 3 by 3 this time. The entries are 0, 0.6, 0.4, 0.2, 0.4, 0.4, 0.4, 0.6. So this will be our transition matrix for this Markov chain. So you guys can check yourself if you want. This does represent a regular Markov chain. If I take powers of this, eventually these zeros will go away. Everything will become positive after enough powers, probably just after taking the second power in this case, I think. So this is a regular Markov chain. And so we can ask, what is the stable vector? So what is the stable vector? It's good to know what the question is that I'm asking. So the question is, what is the stable vector? And so again, we're going to basically go through the same process that we did. So I'm going to write down W equals W1, W2, W3 this time, because I have a 3 by 3. So there are 3 states in my Markov chain. And I'm just going to note that when I add up W1, W2, and W3, I get 1. So they have to add up to 1. Okay. So next, I need to find this equation, W times P minus I equals 0. So I might go ahead and calculate first what's P minus I. Yeah. So P minus I well, maybe I'll write it this way, just to save myself some writing. So W times P minus I. I know what W is. It's W1, W2, W3. And then in here, I can write P minus I. So what's P minus I? Well, I just take this matrix and I subtract the 3 by 3 identity matrix. And so if I do that, this is what we should get. Negative 1, 0.6, 0.4, 0.2, negative 0.6, 0.4, 0, 0.4, and negative 0.4. So this here should be our P minus I matrix. I'm going to multiply it with the W matrix here. So again, I'll leave you guys. You can check my work. I do believe that's correct for P minus the identity. Okay. So now I just need to carry out this multiplication and then set everything equal to 0. So what do I get? And I'm going to sort of write it as a column vector. But here are the 3 entries of our resulting matrix. So basically, I'm just going to take this row vector and multiply by each column of this matrix. So I'm going to get like minus W1 plus 0.2 W2, or multiplying with the first column. Multiply this with the second column. I'm going to get 0.6, or sorry, yeah, 0.6 W1 minus 0.6 W2 plus 0.4 W3. Maybe I should just erase this line here. 0.4 W3. Multiplying with the second column, and then I multiply with the third column, I'm going to get 0.4 W1 plus 0.4 W2 minus 0.4 W3. Okay. So this is the result. These are my 3 results for multiplying this with this. And so now what I'm supposed to do is take each of these and set them equal to 0. So I'll do that, and I'm basically going to just write down my system of equations now. Write down the system of equations. Here's what I get. I get, first of all, I have W1 plus W2 plus W3 equals 1. Always have to include this equation. And now I just take each of these and set them equal to 0. So I have negative W1 plus 0.2 W2 equals 0. I have 0.6 W1 minus 0.6 W2 plus 0.4 W3 equals 0. And then I have 0.4 W1 plus 0.4 W2 minus 0.4 W3 is also equal to 0. Okay, there we go. There's my system of equations. 4 equations with 3 variables. Okay. So one thing to point out again is that do I really need all 4 equations? I should point this out again. Do I need all 4 of these in my system? Do I need all 4? And the reason I ask this is, so, you know, like in that last example, we had 3 equations and we only ended up needing 2 of them. And it's starting to look like maybe in general that's going to be the case. Maybe I could always throw out an equation. And why is that? Because I have only 3 variables. I only have 3 variables. But on the other hand, I have 4 equations. So I have more equations than I do variables. You know, if I was thinking of this as a matrix, I would have 4 rows and 3 columns to the left of the vertical bar. And so if I'm going to end up being able to reduce this matrix, which I am going to be able to, then it's going to have to end up looking like this. I'm going to be able to solve this and find the W's. It's going to have to end up looking like this, and then there's some stuff over here. I don't know. But I'm going to end up with a row of zeros, always. You know, if I could solve these, which